Modern large language models process billions of parameters to write code or generate essays. But if we strip away the massive scale, the core mechanism relies entirely on the relationship between just two discrete data points. The basic problem every language model solves is straightforward. Given a specific sequence of data we have already observed, what should come next? We are going to build a character-level bigram language model from scratch. To do this, we will train our model on a simple dataset of 32,033 names. We will approach this in two steps. First, we will solve the prediction problem manually by counting character frequencies and calculating their probabilities. Then, we will prove the mathematics are identical by rebuilding the exact same system as a neural network in PyTorch. By focusing on how a model predicts a single character based on just one preceding character, we expose the exact mathematical logic required to understand much larger architectures. We start with our training data, a text file containing over 32,000 names. Our first objective is to extract the frequency patterns hidden inside these words. We do this by breaking the data down into bigrams. A bigram is strictly a sequence of two consecutive characters. Let's look at the name Emma. The bigrams present in this name are EM, MM, and MA. But we also need to know where words start and finish. We introduce a special dot character to represent both the initialization and termination of a sequence. So the complete list of bigrams for Emma starts with .e and ends with a dot. This 27 by 27 matrix maps our vocabulary. Using a string-to-integer map, or STOI, every character gets an index. We iterate through the dataset, adding counts to cells for every bigram, directly proving the frequency of specific character combinations. We now have a hard map of character relationships. However, these raw integer counts are simply tallies. We cannot use them directly in a mathematical function to sample and generate new text. To make this usable for generation, we must convert the raw counts in every row into a normalized probability distribution. The values across any single row must sum to exactly 1. We achieve this by taking the count in each individual cell and dividing it by the total sum of all counts in that specific row. Before we divide, we apply add-1 smoothing. By mathematically adding a count of 1 to every single cell in the matrix, we ensure that no sequence receives an absolute 0 probability. An exact 0 would break the loss function we use to evaluate the model later. We build the generation loop using PyTorch's multinomial function, taking the current row's probability distribution to sample the next character. This autoregressive loop feeds the sampled character as the next input, repeating until it predicts the dot termination token. This process successfully generates novel sequences of characters, but raw generation is scientifically useless unless we have a strict mathematical metric to evaluate exactly how well our distribution mirrors the actual training data. To evaluate the model, we calculate the probability of a complete generated sequence. We do this by multiplying the individual probabilities of every constituent bigram in that word. We face a mechanical underflow problem. Multiplying many small fractions produces a number that quickly exceeds computational memory limits. We solve this by wrapping the probabilities in a logarithm, which transforms the problematic multiplication of fractions into manageable addition. We average this resulting sum to get our log likelihood. Since probabilities are fractional values between 0 and 1, this addition produces a negative number. We invert the sign to create a positive metric, negative log likelihood, or NLL. Machine learning optimization relies exclusively on minimizing a loss function. By inverting the value, NLL becomes a positive number that we can actively drive down toward 0 during training. NLL now serves as our objective truth. A lower negative log likelihood explicitly proves that the model is assigning higher mathematical probabilities to the correct true character sequences found within the dataset. Now we pivot from manual statistical counting to a PyTorch neural network. We reframe our extracted bigrams strictly as tensor pairs, the input character array, XS, and the target expected next character, YS. We cannot feed the raw integer indices directly into a neural network. Passing a 2 for B and a 1 for A implies a false scalar weight. It tells the net twice the value of A. We solve this using one-hot encoding. We expand a single integer into a 27-dimensional vector. All positions in the vector are set to 0, except for the single index corresponding to our character, which receives a 1. This diagram outlines the architecture: a single linear layer containing a randomly initialized 27 by 27 weight matrix. For the forward pass, we multiply our one-hot encoded input vectors by this matrix. The output yields our raw logits. These raw logits can be negative or positive, so we must transform them. We exponentiate the logits to create strictly positive equivalent counts. Then, we divide them by their sum to normalize them into a valid probability distribution. Structurally, this neural network is engineered to output the exact same normalized probability distribution that we previously calculated by hand using basic tallying. Looking at both methods side by side, we see the mathematical equivalence. The manual statistical method calculates probabilities as counts plus 1 divided by the sum. The neural network calculates probabilities as exponentiated logits divided by the sum. This final transformation in the neural network is explicitly known as a softmax layer. It perfectly mirrors the manual row-wise normalization we performed on our integer matrix. The network's goal is to use gradient descent to organically adjust its initially random weights. Over time, it refines those weights until they perfectly mimic the explicit frequency counts we found in the statistical matrix. The strict limitation of this bigram model is memory. It evaluates exactly one preceding character to make its prediction, possessing zero context about the overall sequence. But despite that limitation, this precise pipeline, vectorizing discrete tokens, multiplying them by a matrix of learned weights, and optimizing for negative log likelihood, is the exact mathematical bedrock underlying modern large language models.